Welcome to this explainer on the fascinating geometry of circles, where we're going to build our mathematical understanding step by step.
Created by Mindsticks Foundation Trust.
Alright, let's quickly review our lesson plan for today. We'll be looking at circle basics, circles through given points, secants and tangents, the tangent theorem, converse and segment theorems, and finally, applying circle properties.
Section 1. Recalling circle basics.
So let's just quickly jog our memory on some things you probably already know. First up, congruent circles. These are entirely separate circles, right? But they have exactly equal radii, which makes them perfect duplicates of each other. Then we have concentric circles. These share a single central point but have different radii, kind of like a dartboard. And finally, intersecting circles. These are circles that cross each other's paths at two distinct points. Simple enough, right?
Moving on to Section 2. Circles through given points.
Now, before we dive into the rules, I want you to ask yourselves this fundamental question. If you place a certain number of dots on a piece of paper, how many unique circles can you draw that perfectly trace through every single one of those dots?
Well, let's think about it. If we have just a single point, say point A, we can draw literally an infinite number of circles around it. If we have two distinct points, A and B, we can draw a straight segment right between them, and if we use a perpendicular bisector, we'll find that absolutely any point on that bisector can serve as the center for a circle passing through both A and B. So you guessed it, an infinite number of circles can pass through 2 points as well.
But the real magic happens when we introduce a third point. Here are the core rules you absolutely must remember. While 1 or 2 points allow for infinite circles, 3 non-collinear points, meaning points that form a triangle and don't sit on a straight line, they lock in exactly one unique circle. Just one. Furthermore, if you place 3 points perfectly in a straight line, making them collinear, there is simply no way a circle can ever pass through all 3.
Section 3. Secants and tangents.
Okay, the crucial takeaway here is understanding the difference in how these lines interact with the circle itself. A secant is a straight line that boldly cuts right through the circle, intersecting it at 2 distinct points. It just slices right through. A tangent, on the other hand, is far more delicate. It's a line that merely grazes the outer edge, touching the circle at exactly one single point of contact, without ever crossing inside.
So, to visualize this in your head, imagine a line crossing through a circle at 2 different places. That's a secant. But if a line touches the circle at only one single location, it's a tangent. And that specific singular location is mathematically referred to as the point of contact.
Section 4. The tangent theorem.
This is absolutely foundational. The theorem simply states that a tangent is always perpendicular to the radius at the point of contact. Always. And we're going to prove this using an indirect method. Now, in mathematics, an indirect proof means we deliberately assume the exact opposite of what we want to prove. If our false assumption leads to a geometric impossibility, well, then we know our original theorem just has to be true.
Let's walk through the logic step by step together. Step 1. We assume our tangent line is not perpendicular to the radius. Step 2. We invent a new segment and pretend that it is the true perpendicular. Step 3. We place a point C on the line matching the distance of our original point. Step 4. By using the side angle side congruence test, we prove our 2 triangles are perfectly congruent. This means the hypotenuse is equal to the radius, forcing point C to also lie on the circle. And here is step 5, the brilliant contradiction. This means our line intersects the circle at 2 distinct points. But remember our definition? A tangent only touches at 1 point. Our assumption has completely fallen apart. Therefore, the tangent absolutely must be perpendicular to the radius.
Section 5. Converse and segment theorems.
You know, the converse of our theorem is also true. If a straight line is perpendicular to a radius at its exact endpoint on the circle, it simply must be a tangent. Consider this. Any other point on that line creates a right-angled triangle where the new line segment is the hypotenuse. The hypotenuse is always the longest side, meaning it's longer than the radius. And because it's longer than the radius, that point must sit completely outside the circle. Only the exact perpendicular point touches the circle. Makes sense, right?
And this leads directly into the tangent segment theorem. If you take a single point completely outside the circle and draw tangent lines that touch the circle at 2 different points, those 2 tangent segments are perfectly congruent. They form perfect symmetry, being exactly 100% equal in length.
Section 6, Applying Circle Properties.
So, why does all this abstract geometry matter in the real physical world? Well, think about riding a motorcycle on a wet road. As the tire spins quickly, water droplets splash off. Those droplets travel exactly along tangent lines. The very same physical rule applies to the glowing splinters escaping a spinning Diwali firework, or the bright sparks flying when a metal knife is pressed against a rotating sharpening stone.
Physics beautifully illustrates our geometric theorems right in motion. The rotational inertia of the wheel throws the water and sparks perfectly perpendicular to the radius at the exact point of release. Geometry isn't just lines drawn on a page. It's the invisible framework governing exactly how physical matter behaves in our universe. It's literally everywhere.
Let's look at a practical application of this. If the radius of a circle is 6 centimeters and a line forms a tangent at point A, what is the measure of the angle formed? Thanks to the tangent theorem we just proved, you instantly know, without a single doubt, that the angle is exactly 90 degrees. Knowing this 90-degree anchor allows you to use Pythagoras' theorem to calculate any other distances you might need. It's a real game changer for solving these problems.
I'll leave you to ponder this final thought. How can you apply this infallible 90-degree tangent rule to solve complex distance and angle problems in your own upcoming studies? The tools are now in your hands. Thank you so much for joining me in this explainer. Keep practicing, and always stay curious about the mathematics all around us.